So last lesson you drew for me the Cassegrain arrangement for reflecting telescopes. So I'd like you to see if you can still remember how to do that for me. So can you quickly draw it for me? Pause the video, have a go. Okay, and this is the arrangement you should have. Your mirrors with the lines on the back showing the direction. Your two rays coming in. Dotted line to show where the focal point would be, projected rays. The rays coming off, crossing in the gap in the middle, hitting a lens and then becoming parallel as the rays coming in were parallel. Lovely. Okay, so what else do I want you to look at with reflecting telescopes? Well, I want you to know how to calculate something called the resolving power of a telescope and be able to compare the refracting and reflecting telescopes. So resolving power of a telescope is sometimes called the Rayleigh criterion, okay? It tells you if for your telescope how far apart the two objects have to be before you can see them as two separate objects rather than one. And it's different for different telescopes. So say like you had two stars quite distant, at what point could you tell they were two stars instead of just one? So it's a measure of the detail you can see. Now it's dependent on something called the minimum angular resolution. So that's the smallest angular separation. So it's not the distance between them, it's the angle between them that's measured. So if these are my two stars here and here, the angle between them is here, yeah? Or if the telescope is here, it would be that distance there, okay? So it's the smallest angular separation at which the instrument can distinguish 2 points. Now resolution is limited by diffraction. So as the light comes into a telescope, because it's a hole, the light will diffract and spread out, and you get diffraction patterns, single slit diffraction patterns. So as the light passes through a circular aperture, you get diffraction, and the central circle is called the airy disc. So I'll just show you what that looks like. So if this is my telescope here, and the light comes through, so the wavefronts are parallel, so they're coming in like this. As they come through the gap, they diffract, like so. So they bend. So you get a single slit diffraction pattern. Now if you remember from AS, a single slit diffraction pattern has a central maxima, okay, and then the resulting minima around it are smaller. So this is twice the size of these bright fringes. So the central fringe is twice as wide as the other fringes. I've probably not drawn that very well there. And then they go on the other side too. Let me just draw that a bit better because that is terrible. So you have a central fringe, okay, that's twice as wide as the other fringes, and they're dimmer as well because they're further away. So that's the diffraction pattern of a single slit. Now what that looks like in your telescope is called, well, the central maxima is called an airy disc. And then you get a minima. Then the next maxima is dimmer, but it's also like half the size. You don't really need to draw it half the size, you just need to draw it smaller than the airy disc. So you get this sort of pattern. Yeah? I'll just show you what that looks like in a real telescope image. So this is what it looks like in a real image. So you get these like black lines you can see. Okay? And then you have the central airy disc. So how does this relate to resolution? Well, two light sources, e.g. two stars, can just be resolved. Okay, so you can just see them as two separate objects when the first minimum of the airy disc of one image coincides with the central maximum of the airy disc of the other image. So you need to know this, you need to write it down, you need to highlight it and put a big box around it and learn it off by heart. What does that look like? Well, if this is my first object, the yellow one. And then the orange one is my second object, so that's coming in too. And then it's diffracting. So if this is my yellow one here, you will only get to see the two objects if the maximum of the second one is in the first minimum of the first one, if you like. So here, minimum, so you get your maximum here, and then comes down, and then you get your other patterns. It's hard to draw the whole pattern, but you can see they coincide. It's really hard to draw it on this, but basically the center of your maximum is where this minimum is, so it's like there. Yeah. So the maximum of the second object is in the first minimum of the first object. Let's go back to this. Two light sources, e.g. two stars, can just be resolved when the first maximum of the airy disk of one image coincides with the the first minimum of the airy disk of one image coincides with the central maximum of the airy disk of the other image. Okay, which is what I just showed you. Now the Rayleigh criterion tells us, okay, how resolved an object is. So the Rayleigh criterion, theta, is the minimum angular resolution. Okay, and it's approximately the wavelength divided by the diameter of your aperture. Now you can see if you have a greater D, then this angle is smaller, which means you can see greater detail. So the Rayleigh criterion, theta equals lambda over D. If we have two telescopes and one has a D of a diameter of the aperture as, I don't know, 5 centimeters, and the other one has 10 centimeters, and you're looking at a wavelength of 500 nanometers. Let's look at the wavelength, the Rayleigh criterion. So number one would be 500 nanometers divided by 5 centimeters, and number two would be the same wavelength of light, but it's 10 centimeters. Which gives me this answer. So this one can see down to 1 times 10 to the minus 5 radians, and this one can see down to 5 times 10 to the minus 6 radians. So this can see a smaller angle than this one, which means this one has a better resolving power because it can see two objects that are closer together. The distance between those two objects is greater than the distance between those two objects. In fact, in this case, because this is 5 and 10, they're twice as far apart, or the angle's twice as big than this one. Okay, so the way we would describe that is we would say number two has a greater resolving power because it has a smaller angle of resolution, or you can call that Rayleigh criterion. Okay. Something else called collecting power. So collecting power is how much light you can actually collect. So let's say I've got my two apertures again. One's 5 centimeters, one's 10 centimeters. Which one of these can collect more photons? Well, of course it's this one because it has a greater area. So if our diameter, okay, the collecting power is proportional to diameter squared because of the area, okay? So the area is pi diameter squared over 4, okay? So this one has a greater collecting power because its diameter is greater, so you can collect more photons. Should we see how much its collecting power is greater? So because it's proportional to d squared, if we do 10 squared over 5 squared, we get 100 over 25, which is 4. So its collecting power is 4 times greater. So you can do this calculation and you could say, so you would say collecting power is proportional to d squared, and the collecting power of number 2 is 4 times greater than the collecting power of number 1. So that means it's 4 times brighter. So a greater diameter is good, okay, because it allows you to increase your collecting power with d squared. So that's great. I mean, double the diameter, you get twice as much light, which is, 4 times as much light. Brilliant. But it also allows you, because the Rayleigh criterion, the resolving power is proportional to 1 over d. Hello. Yeah? The greater the diameter, the smaller the Rayleigh criterion of the resolving angle, which means you can see things closer together. Okay? Right, great. Let's make some absolutely massive telescopes then, shall we? Well, that comes with its own problems. So you want a big telescope, brilliant, but it comes with some issues. So we're just going to go through those issues now. You can just watch it and then at the end write down the table if you like. So what are those issues? Well, refracting telescopes, they have something called chromatic aberration. Basically, glass diffracts different colours by different amounts, different colours by different amounts. So that's a refracting telescope. So that's the first telescope we did with the 2 ray diagrams, got 2 lenses in it. So different colours get refracted by different amounts. So basically you get each colour in a different position on an image. Let me show you what that looks like. So this is an image of the moon, and you can see you get this weird light. So the red light's here and the blue light's here. Okay, so that's chromatic aberration. This is you can get asked to draw chromatic aberration. This is how you do it. You draw the lens and then you draw the red light refracted least and the blue light refracted most, and draw the central line through the middle. You don't have to draw the green light, but you need to draw the central line through the middle. Because you're doing it on an exam paper, you'll be doing it in black and white, so you need to label that one red and that one blue. You make sure they cross on that central point, and that's the image. Chromatic aberration. Right, refracting telescopes also have impure glass. So the bigger your lens, the more impurities. So bubbles and impurities in glass absorb some of the light, which means that faint objects cannot be seen. So it's difficult and expensive to build large lenses of good quality, like really expensive to build big lenses. Okay. Distortion. Large lenses are heavy and they can only be supported at their edges, so their shape can be distorted. Because you need the light to go through the center, you can't support them here. So because they're only supported around the outside, they sag. So that can lead them to get a distorted image. And you also, if you want a large magnification, as you know, you need a long objective focal length. So you need to put these in a big building then, because you need that focal length, because magnification is FO over FE. The bigger FO is, the focal length of the objective lens, the better magnification you get. So you need to put them in a big building, and that's expensive. Okay, so what about reflecting telescopes? Well, reflecting telescopes still get spherical aberration. Okay. Which means that the shape of the mirror isn't quite parabolic, so it's not quite right. The rays don't converge onto the same point, and this makes a distorted image. You can see here it actually shows you the airy disk quite nicely here as well. You get you can get some distorted images. This is what happened to the Hubble Space Telescope. someone put a washer on the mirror grinder on upside down or something, and it was a very small part of the grinder that was wrong, and it made the mirror distorted, not quite the right shape. So when it went up, it saw distorted images. Let me just see if I can find one. Yeah, so here you go. So this is no aberration, and then you get this like fuzzy image. So when Hubble did this, the Hubble Space Telescope, it had to have basically a pair of glasses fitted to it to get rid of that, which cost an awful lot of money, as you can imagine. I suspect the person in charge of the grinding machine was in for a lot of trouble. Okay. But reflecting telescopes do have a good thing in that it is cheaper to build a good quality large mirror. And because you only need the one side of the mirror, you don't need this back bit because the light's not going through, you can support them underneath as well. So you don't get that distortion here. So generally reflecting telescopes are used nowadays. Okay. Right, just write this up, and then I've got some questions I want you to do. Okay, so the questions in the classroom, they're here, and I'm going to go through the answers with you in a minute. So if you pause the video, and then I'll go through the answers. I'll also put the answers in the classroom for you. Okay. Okay, so the question says, the Clyde Observatory in Northumberland includes 2 optical telescopes attached to the same mount. So that they can be used to view the same object. Some of the properties of the telescopes are summarised in the table. So you've got telescope A, that's a refractor, both refractors, they've got 2 lenses, and the diameters are 70 millimetres and 400 millimetres. Telescopes are used to look at the same object. Suggest which telescope produces the brighter image. So we are looking here at collecting power. Okay, so we would say it's B, because it has the largest diameter. Okay, and we would say collecting power is proportional to diameter squared, because it's that area that we were talking about. Then you can find out how much better it is. So if we do B divided by A, we can say, okay, well, we'll do 400 squared divided by 70 squared, which gives me about 33. So it would be 33 times brighter. 1, 2, 3 marks. Okay. Then it says the minimum angular resolution telescope can be determined using the Rayleigh criterion. Explain what is meant by the Rayleigh criterion. Okay, this is where you need that definition. So we start with, it's only worth 2 marks. Okay, it's when 2 objects will just be resolved. Okay, when the first minimum of the airy disk of one image, 1 mark, coincides with the central maximum, spelled with wrong, the central maximum of the airy disk of the other image. I mean, the key points it's looking for is resolved, first minimum, airy disk, central maximum, secondary disk. I mean, they're the key points it's looking for. You can check on the actual mark scheme for what you have to say. So learn that off by heart. I know it's difficult. Okay. If it helps, I just sketch myself a little picture to remember it. So I draw that central maximum, and then I draw a line up in the first minimum, and then I draw my other one there. So it helps me think about the maximum and minimums. Next question. Discuss which of the two telescopes in the table would be better at resolving the images. So resolving is the Rayleigh criterion. So it's going to be B because it has a larger diameter. Okay. We can write out the Rayleigh criterion. You can figure it out if you want. I don't know if it tells you the wavelength of light. No, it doesn't. But you can just then say for the third mark, the smaller the angle, then the better the resolving power. You can figure it out by a ratio as well. So if you did 700 divided by 40, is it 700 or is it, oh hang on, I've lost the sheet. No, 400 divided by 70. It's 5.7 times better. So you can see things that are 5.7 times closer together or 6 times closer together. Right, then for the second part, draw the diffraction pattern produced when light from a star passes through a circular aperture. So it needs that airy disk. Now, because it would be in black and white, with your pen, you have your central maxima, draw it white, okay? Then you have a minima, so you need to just draw a ring around it and then colour it in black. Then you'll need your next maxima. It only wants to compare to, so you don't need to do another one after. But your next maximum has to be about half of that, so this wide. It doesn't matter if it's not exactly half, but it definitely has to be less than the middle one. So you can have that, and then if you wanted to draw another black ring around it, you could. Okay, and that's because this maximum in the centre of a single slit diffraction pattern is twice as big as the next ones. Okay, explain what is meant by the Rayleigh criterion for the resolution of two stars. So basically it's this, what we said here. Two objects will just be resolved when the first minimum of the airy disk of one image coincides with the central maximum of the airy disk of the other image. If you want to draw an image, you can draw this one. Okay. And then it says a star A-Rich in the constellation Virgo is two stars separated by an angle of 1.1 times 10 to the minus 5 radians when viewed from Earth. So that's that angle there. Okay, so here's you with your telescope looking at them. Calculate the minimum diameter of the telescope. So how wide does this telescope aperture have to be to observe star of wavelength 5.7 times 10 to the minus 7 meters? So if we do our Rayleigh criterion equation, it's that, but I want D. So D is lambda over theta. So it's 5.7 times 10 to the minus 7 divided by 1.1 times 10 to the minus 5, and it gives me an answer. Remember, this is approximation of about 5.2 centimeters. So if you were making a telescope, this would be a good size to use to get good resolution, but it's a balance then between the collecting power as well. Okay, right. Hopefully you got on with them. If you've got any questions, you're more than welcome to email me.